let's do some practice calculations with spin now that we have multiple directions to think about, the z direction and the x direction. If you want, you can just pause this video, looking at the screen right now, and try and work these out on your own, and then come back and work through them with us together on the video. Okay, so let's say we start in a down state, so our particle is in a definite eigenstate of spin z, so it's in down. What is the expectation value of the spin in the x direction? Well, again, this might seem like a strange question, so we know that the particle has spin down, and now we want to know what would we get. What is the expectation value, the average value that we would get if we were to measure the spin in the x direction multiple times? Well, so in order to do this, we need the relationship between spin up, spin down, and then the spin right and spin left states. And so we're going to write our spin down state in terms of our spin right and our spin left states using this dictionary that we have here. And so we can first calculate the action of the spin in the x direction on our spin down state, on our state psi. And we notice that, well, when it hits the spin right state, we get a positive h bar over 2. And when then the sx operator hits spin left, we get a minus h bar over 2. There's already a minus sign, actually, from spin down, the relationship between spin down and spin left and right. And so ultimately, those two minus signs will cancel, gives a positive h bar over 2 there on the spin left. Because of this, we see that the spin x direction acting on psi is not, psi is not an eigenstate of spin in the x direction, because we don't get back a number times what we started with, since it flips the sign on the spin left. Okay, so now let's take the expectation value. Figuring out how Sx operates on psi was the first step for calculating the expectation value, because now we need to sandwich in the other bra version of psi with Sx operating on psi. And so let's act with the bra version, take the bra version of psi, and operate that on Sx times psi, giving us ultimately a number out of this. And so we see again that we only pick up terms where we have right overlapping with right and left overlapping with left, because right and left states are again orthogonal. And so in principle there are those terms. I just didn't write them because they're orthogonal to each other, and so their inner product is 0. The inner product between right and right is 1. Same thing for inner product between left and left. And so ultimately I end up getting 0 for this expectation value in the x direction, because there's that relative minus sign there. And again, maybe that's not too surprising if we think about it. So looking at the relationship between the down state and how we write it in terms of right and left state, we see that you get a 50-50 probability of getting a spin right or spin left. And so since you get a 50-50 probability, if you were to make a bunch of measurements of the spin in the x direction, and then average the results that you get, well, it would all average out so that the net spin, or the average spin, would be 0, although any individual spin that you measured would be either right or left. Let's say we do something else with spin, and namely we take this down state, we make a measurement now of spin in the x direction, and we obtain a result of positive h bar over 2 for that individual measurement. What's the probability that we would get a value of minus h bar over 2 in the z direction? So what's the probability after making our measurement in the x direction that we would get spin down? So it seems like we started in a down state to begin with, so it seems like we should get spin down after that measurement, but that's not quite how quantum mechanics works, and so we need to be a little bit more careful about how we approach this. So remember, after you make a measurement of a quantity, the wave function will now change to be an eigenstate of that quantity. So we made a measurement of spin in the x direction and obtained positive h bar over 2, which means after our measurement, our wave function changed to become spin right. It's no longer spin down, the wave function is now spin right. In order to answer the question of what is the probability to get spin down then, what we need to do is find out what is the inner product between spin down and our new wave function psi. Or said another way, what is the inner product between spin down and spin right? Since now our wave function is spin right after our measurement. Well, we don't have a way of writing spin right in terms of spin up and down yet, but we can get there actually from our expression up above. So let's rewrite the relationships that we have up above between spin up, spin down, spin right, and spin left. I'm just going to rewrite them here. And you notice if you add these two, then the spin left terms will cancel each other. The spin right terms will add. And so I get something that looks like spin up plus spin down is equal to 2 over the square root of 2. 2 because I added those terms on the right-hand side, times spin right. Or just reorganizing, spin right is equal to 1 over square root of 2 spin up plus 1 over square root of 2 spin down. So spin right is itself an equal mixture of spin up and spin down. Well, that's what I needed, though, in order to do this inner product between spin down and spin right. And so inserting what I have for spin right here into my absolute value squared, and then including that spin down bra and doing the inner product, I get a term that looks like an inner product between spin down and spin up, which I'm going to write explicitly here, just to point out that that inner product is 0, since spin down and spin up states are orthogonal. And then I also get a term that is spin down with spin down, with a coefficient of 1 over square root of 2. So when I take the absolute value squared of everything inside, after simplifying, I just get a probability of 1/2, or 50%. And again, if we think about that, there's something funny going on here. So we started in a down state. We made a measurement, and then when we made another measurement to see if our particle is in spin down, or what is the probability of getting it in spin down, now instead of being sure that we're getting a down state, now we're getting a 50% chance of getting spin down. So that's kind of strange. So the active measurement changed the wave function so that even though we started in a down state, after we made that measurement, we now have a 50-50 chance of getting either spin up or spin down. Okay, so this is just the weirdness of quantum mechanics showing up here. But this is how we would represent that in the math of using Dirac notation and doing the calculations.